I got to record for those that aren't here. Okay, recording, sharing. And let me tell these people to get registered. Ooh. This thing. All right. Okay, let me say this again about registering. So I do encourage you guys to get registered if you're going to be taking the class this spring, and I will be giving some bonus points to people who do register, I'll say on a timely basis, probably by sometime next week. So please go on and do that. Now, today we're working up to the last test, which is going to be a week from today. And did you guys get the practice set of problems?
Yes.
Yeah. Yeah. Here I had copied it in orange here, whatever this salmon color here. I made up the test yesterday. It has 15 questions on it, and what I can say is this. Actively, as I put in big letters on the board here, actively work the practice set, all right, and you should be in good shape. And the key word, one of the key words there is actively work the practice set. The solutions will be posted on Blackboard Sunday afternoon, but I want to discourage you from just looking at the solutions and following along on the solutions. That's a passive way of looking at the problems. And you may then, when you're actually doing, if you do that, only that, and then when you're taking the test, you may then wish that you had actively done the problem rather than just look at it, because there's a different kind of learning that goes on when you actually work the problem and maybe make a mistake and then check the solutions and go from there, all right? But that practice set is certainly key to doing well on the test. Okay, and then on Wednesday, then there's the last homework and the take-home quiz are due that day also, okay? All right. So we're talking here about conic sections. It seems like this topic will never get over it. And in this last section, 10.6, we're talking about writing the equation for a conic section using polar coordinates. So we're going to use polar coordinates to write the equation of each conic section. Okay. Now, with doing this, we're going to, there are two things that we use. We have to have a focus, and the focus that we're assuming to have is at the origin 0, 0. So we assume, because this makes the expression algebraically much simpler. Assume that a focus is at 0, 0. And also, with all of these conic sections, they all will have what's called a directrix. Up to now, we've only looked at the directrix in terms of the parabola, but all three of these will have a directrix. And so we have a directrix also. And that's a straight line. Okay. So the basic theorem here behind this, I had put this up last time, but we want to start again with this for today. And so the theorem is this. We'll call capital F, we'll call that focus at 0, 0. Fixed point focus at 0, 0. And we're going to call small l, let small l be a fixed line. And that is what we are going to be calling the directrix. Then we have this, the set of all points, and we'll just call them capital P, such that the distance from the point to the focus divided by the distance from the point to the straight line, so I'm just using that abbreviation with absolute values to indicate distance, is equal to E, and this is not the E that we have been using, the 2.718. This is not the natural log E. It's just the small lowercase e. So basically what we're saying is this: the ratio of their distance, the point's distance from that fixed point F to their distance to the fixed line L is going to equals a positive constant that we're calling little e. So I'm just writing in English what that equation says. So I haven't really finished the sentence here. So we've got the set of all points on this shape such that the distance to this focus, that's at 0, 0, over the distance to the straight line is equal to e. So what about these set of all points? Well, this is the case. Is 1 an ellipse? These points are an ellipse if that e is a number between 0 and 1. Actually, yeah. I technically could put an equal sign there by the 0. And if the parabola, those points are a parabola, if that e is exactly equal to 1. And number 3, it's a hyperbola if that e is bigger, strictly bigger than 1. All right. This e is called the eccentricity. And what I can tell you here about the eccentricity is this. This e is a number that goes from 0 all the way, I guess it go all the way up as big as it likes to infinity. And basically, the closer this number is to 0, the closer the figure looks like a circle. In fact, at 0, it is a circle. Then as e moves away from that, it becomes this ellipse. When e equals 1, that ellipse breaks apart, so to speak, and it becomes a parabola. And then when e is bigger than 1, the parabola breaks up to become 2 parts, a hyperbola. And if we went all the way to the limit of infinity, the points would all end up being a straight line. So this e, this eccentricity, one way of thinking about it is that it measures how far off from being a circle the conic section is. It basically goes from a circle all the way to a straight line, depending on the value of the e. All right? Okay. Now, what I want to do here then is just go through some diagrams for basically the 4 basic cases here that we're going to have. We're going to either have our conic section be oriented horizontally to the left or to the right, or we're going to have it represented vertically going up or going down. All right. So let's look at case A here. And with case A, and this one I had put on the board before. All right, let's draw our axis here. And remember, we are assuming that one of a focus is at 0, 0. So right here, capital F, that's our focus at 0, 0. Now, in this case A, I'm assuming that our directrix is over here, and in this case, it's a vertical line. So it's x equal to the number d. So this is our line small l that we call the directrix. All right. And d here is bigger than, it's a positive constant, bigger than 0. All right. Then, I'm terrible at drawing, but here we're going to have our conic section, maybe something that might be looking like this. And let's pick a point on the conic section. Remember, in the theorem, we call these points P, capital P. All right. So what the theorem is saying is that this distance here from P to the focus divided by the distance from P to the directrix line. So this would be a right angle right here that it would form. That ratio is equal to E. So let's look at this in terms of, remember this is going to be all about polar coordinates. So let's look at this in terms of polar coordinates. Okay. First of all, the distance from that point P to that focus that's at the origin, we can call that R from polar coordinates, that distance from the point to the origin, okay? So that's our PS. Now our distance from that point to the directrix line L, well, I'm going to do it this way. I'm going to take the distance all the way from the y-axis to the line L, which is the distance of D. But then I have to take away the distance right here. Now the distance right there is basically the x-coordinate of that point P, all right? So that distance there is going to be r times the cosine of theta, where theta is this angle right there. So I'm taking away that distance from the y-axis to the point, which is going to be r times the cosine of theta. And so what the theorem says is this, that PF over PL is equal to E. And so let's just substitute here. PF then is R. PL is D minus R cosine of theta. And that's equal to this constant E. Now I'm going to do a little algebra here to solve for strictly R on one side of this equation. So we can have a polar equation. So first of all, let's just multiply by the denominator here. So I have R equals E times D minus E times R cosine of theta. So I've just got rid of the denominator. Now let me get all the R stuff over onto the left-hand side. So I'm going to add R plus E times R cosine of theta equals E times D. So I get that. And then on the left side, I have an R that's common to both of the terms, so I'm going to factor that out. So that's R times 1 plus E cosine of theta is equal to ED, like that. And then finally, I will then divide by 1 plus e cosine of theta, and I get that r is equal to e times d over 1 plus e cosine of theta. Right. All right. Now I'm going to start giving some tips to help you remember these formulas here. Notice here that this is first of all, this is a horizontally oriented ellipse. Okay, it's facing out in the, actually it's facing out to the left, right? Okay. So it's horizontally oriented. So what we associate with going this way or this way is the x-coordinate, right? All right. And what in polar coordinates, what we associate with the x-coordinate is the cosine. All right. So therefore, here in our formula, horizontally oriented, we have the cosine down there in the bottom. Right. Okay. Now, from there, and then what else do we have? We have that our directrix up here, let's go right up to our directrix is x equals d, and I can think of that as x equals positive d. Remember, d here is a positive number, so our directrix is x equals positive d, and notice here in our formula, we have a plus sign down here in the denominator. Okay. Now, also, if our directrix is a positive valued vertical line, our conic section is going to be going in the other direction from that line. So we can see that since d is a positive number, since x equals d is our directrix, which is positive, this thing is going to be going to the left, to the other direction. So therefore, it'll go to the left. All right. And I'm going to be doing a similar thing with the other cases, and then finally I'm just going to sum them all up in like one single diagram for you guys. Now, as an FYI, in the text, they go through, they basically take this formula and convert it back into the x and y coordinates, Cartesian coordinates, and they prove that this indeed is equivalent to the conic equations that we had in x and y. All right, I'm going to admit that, and so you can read that if you like on your own. But this indeed will end up being equivalent to what we had seen in the previous section in terms of x and y. But now it's in terms of the polar coordinates. All right, so that was case A. Let's then look at case B, where we're going in the other direction. And in case B, so we have our x and y axis. And here we're assuming that one of the foci is right here at 0, 0. All right. And now we're assuming then that it's going to be horizontally oriented, but now we're looking at it going this way. So over here, on this side, we're going to have that directrix vertical line. Now this vertical line then is going to be x equals negative d. We're always assuming in all of these cases that d, that small d, is a positive number. So this is over on the left where the x's are negative. Now again, we're going to apply that theorem. So we take any point here on the conic section, and we look at the distance it has to the focus, and we look at the distance it has to the vertical line, the directrix. Okay. Again, the PF, the distance to the focus, is going to be R right here. Now this, however, this time the distance to the straight line is a little bit different. First of all, right here, the distance that we have right there from that vertical line to the y-axis, that's a distance d right there. But then on top of it, we then have to go further to get the full distance. And this component here is again the x component, and it's going to be r cosine of theta, where this angle here is theta. So now this distance PL is going to be d plus r cosine of theta. Previously it was d minus r cosine of theta. And then again we look at the ratio of PF over PL, and that's going to be equal to our number E. And so I substitute again for PF, I have R. For PL, I have D plus R cosine of theta, and that's equal to E. And again, I do the same kind of algebra manipulation in order to isolate the R on one side. So I'm going to again multiply by the denominator. So R is equal to ED plus ER cosine of theta. Get the R's on one side. R minus ER cosine of theta is equal to ED. Bring out the R that's common to both. So that's R times 1 minus E cosine of theta is equal to ED. And then divide. So I get R is equal to ED over 1 minus E cosine of theta. Yes?
What is the point on the other side? This is why we're negative. What if the point was on the left side of the...
It would still work out. In other words, what if the point were here?
Yeah.
Okay. Let's see what we would have there. All right, the distance then from here to here would still, the distance of PF would still be R, right? All right, and here PL then, what would PL be? Look what we end up getting. Remember, all students take calculus, our 4 quadrants. If we're talking about here, and we're talking about r cosine of theta, our angle here now is in the second quadrant, right? Is that correct? So in the second quadrant, the cosine is going to be a negative value. What we're going to end up getting here is we're going to get that it's equal, this distance here to here, that's the distance of PL. That's going to be the whole distance D minus the x component right here. And because the cosine will be negative, that will subtract it off. So it still will work. And it's because the cosine here in that second quadrant is negative. It will still work because it'll then subtract it. You buy in that?
Well, there's a plus sign, so why would we want to subtract it? Yeah.
We want to subtract it because the formula is we just want this distance here from the point on the curve to the directrix.
Right, but that distance is plus.
It does say plus, but because our cosine is going to, in that area, is going to end up being a minus, it will truly give us the distance, even though right here that certainly does say a plus. But my cosine will be minus, So it will end up being the distance from here to here, because it's going to be the full distance minus, and it will have a minus because the cosine is negative, minus that little distance there. You buying it now? All right. Okay. So what do we have here? Again, here's our formula. Again, it's horizontally oriented, and notice we have the cosine, which is associated with x, so that's a clue that we're horizontally oriented. Did I say this on here? Yeah, okay. Now, notice this time we have a minus here. What is our directrix here? Our directrix is x equals minus d. We're always assuming that that little d is a positive number. So our directrix is x equals minus d. That minus can be seen as corresponding with that minus that we have down below. All right? These are just little tricks to help you remember the connection. Because some of the things you'll be asked is what's the equation of the directrix, that type of thing. So this will be a clue. It's going to be a minus in front of it. All right. And then, since our directrix is a negative number, x equals a negative number, this thing is going to be oriented the other direction to the right. Since x equals negative d is directrix, it will be oriented the other way to the right. It'll be oriented to the right this time. Okay. And that's our second case. Yeah? Mm-hmm.
These questions have to find whether it's right or hyperbola.
Not quite just that. All right. We'll be going through some examples after we just run through these cases, okay? All right. Also, so the question is, what will you only be asked, is it an ellipse, parabola, or hyperbola? And the answer is no, not just those. That will certainly be one of the questions that you would be asked. But we'll go through some examples. Also, I know that have you guys completed the take-home quiz yet? No? Okay, I'm just kidding. I know you haven't completed the take-home quiz. But if you look at the take-home quiz, there are some problems here on that. And you'll see let's see, where's this take-home quiz? Oh, yeah. So here, let me just put this up here. So here we're given R equals something or another, okay? And notice there's 5 different types of questions that we can ask on this. So we're going to get to that with some examples, all right? Okay. All right, let's then go to case C here. So far we've looked at horizontally this way, horizontally the other way. Now we're going to look at vertical. And then we'll summarize this. So for case C, we're going to have this kind of situation. Here's our axis. Remember, our focus is always, we're going to have that right there at 0, 0. Except now it's going to be going upward. So our curve's going to be looking like that. And our directrix is going to be over down here on the other side. Now, in this case now, our directrix is a horizontal line. So it's going to be y, and it's down below the x-axis. It's going to be y equals negative d. We're always assuming d is positive. Okay. Now, basically, let's just take any point here, capital P, and apply the theorem here. So again, we look at the distance from P to the focus, and that's going to be R. And then we look at the distance from P to the line. So that's this whole distance right here. And that's going to be, first of all, the distance from the directrix to the axis. So that's going to be capital D. And then we're going to be adding on a little bit right here. But now what we're adding on is the y-coordinate portion. And that's connected with the sine. So we're going to be adding on plus our sine of theta. And this will work also if the P is down below the x-axis for the very similar reason as what we had talked about before. So let's apply the formula PF over PL equal E. So that's going to give us R over D plus R sine of theta is equal to E. And I think I'll spare you guys just those couple of algebra steps. It's just like the algebra steps I did in the first two cases. So what we come up with is this. We isolate the R on one side, and we again have E, D on the top, E times D. And then on the bottom, though, we have 1 minus E sine of theta. All right. Now, this is a vertically oriented conic section. So we want to remember we're going to be connecting that in our minds with the sine, which is connected with the y coordinate. Our directrix in this case is y equals minus d, and that is going to be connected with the minus that we have down below in the denominator. Okay. And again, because our directrix is y equals minus d, it's going to be oriented upward, like that, the other direction. So that's case C. The last case then is just a vertical where it's going downward. And I'll put all these up as a summary once we're finished with this last case. Case D then is again vertically oriented. Here we have the focus at 0, 0. This time it's downward. And so the directrix is going to be up here. And that'll be y is equal to plus d. Again, d is considered positive, greater than 0. All right, same deal. We take a point here, and we look at the distance to the focus at the origin, and we look at the distance to the directrix. And so we have PF over PL is R over, now this time it's going to be what? Okay. Here we're going to have 2 points to it. Right here, the distance from the point to the directrix. First of all, we've got the D distance there from the x-axis up to the directrix. And then we have this other portion down here, which is the y-coordinate. So this distance PL is again going to be D plus R sine of theta, like that. Okay. And that, and that all is equaling E, our eccentricity. So again, dot, 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 do the algebra. Yeah, Jenna. Let's see. Did I mess up here? Okay, our point distance here is going to be, no, I think, we're going down. So first of all, we have this distance. So the distance here, we have this distance here, which is d.
Because it should be minus and then a sign.
Mm-hmm.
So it's in the same spot.
Mm-hmm. Yeah. Right. Okay. You're right. Yeah, because here, if the point were here, it would be the whole distance and then minus that. Yeah. Okay. Let's go with that. Right. Sorry about that. Okay. So we have r over d minus r sine of theta, and then that equals our e. Then let's solve for r here, and let me go on and do this. So we have r is equal to e times d minus e times r sine of theta. I don't think wait a minute. Yeah. Oops. Yeah, that's right. And then we, And then we get r's on one side, so we have r plus er sine of theta is equal to e times d. Isolate the r times 1 plus e sine theta is equal to ed. And then divide, we get ed over 1 plus e sine of theta. And that's correct. Okay. So, okay, again, let's look at this. This is vertically oriented. And we have the sign here at the bottom. The directrix this time is y is equal to plus d. And notice the plus here corresponds to that right down there. And then again, it's going to be downward oriented since y equals plus d is the directrix. Okay. All right. So let's summarize then in kind of maybe on one page here, what we've got in these 4 cases. Any question here before I get started on the summary? All right. So here's summary. All right. And we have these 4 cases. All right. First of all, let's look at horizontally oriented. Again, remember always, the focus, one of the focus foci is always considered to be 0, 0. And E is bigger than 0, and D is also bigger than 0. So, if we have it like this, if we have R equals E times D over 1 plus E cosine of theta, basically we then have X equal plus D is the directrix. It's going to be horizontal because of the cosine, and it's going to be going to the right. To the left. So it's going to be something like this that I've drawn before. Here's our focus. It's going to be going this way, and here's our directrix. X equals D. All right. Then the other direction. R equals E times D over 1 minus E cosine of theta. This time our directrix is X equals minus D. Notice the relationship there with the pluses and the minuses. The cosine, again, it's horizontal orientation because we have the cosine there. And this is going to be to the right. So the drawing then is, again, the focus right there. It's going to go to the right, and our directrix is going to be over here to the left, x equals negative d. So those are those two cases. Then we have the vertically oriented. And this time it's going to be, again, it's going to be r equals ed. Notice it's the same thing on the top all the time. E times d. E is the eccentricity, d is the directrix. And then one case is going to be 1 plus e sine of theta. And then here, our directrix then, first of all, this is going to be vertically oriented. We've got the sine. And our directrix here is going to be plus d. But this time, because it's vertically oriented, it's a horizontal line. It's y equals plus d. And it's going to be going up. No, it's going to be going down, sorry. And it's like this. We have the focus here. It's going down. Here's our directrix here. Y equals plus d. Okay. And then finally, r equals e times d. 1 minus e sine theta. Because we have a minus, it's y equals negative d, negative number. Again, the sign makes it vertically oriented. And this is going to be going upward. Focus is here, curve is here, directrix is down there, y equals minus d. And if you look on this, things to know for test 4, basically on the last couple of pages, where is it? That's actually on the very last page. On that page 7 of this thing, I basically have this all summarized with the either the vertically or the horizontally oriented. Okay. One thing that's interesting, so now the whole deal with these, let me put this down here at the bottom of this page, because I haven't emphasized this enough. We're trying to have this E, this eccentricity. So if this curve will end up being an ellipse if the E is between 0 and 1. Well, actually, if it's actually equal to 0, it'll be a circle. If it's exactly equal to 1, this curve will be a parabola, if our E is equal to 1. And finally, it's a hyperbola if E is bigger than 1. So one thing that I thought about was, we know that with a hyperbola, we have two different sections to it. So I was thinking, so how can this simple equation like this for a hyperbola end up generating two different sections? Does anybody have an idea? Is this a question or an idea?
Maybe an idea.
Okay. Mm-hmm.
It has like, some of them have like a square root, like the cosine of the sine of the square, it could be plus or minus.
Well, certainly the sine and the cosine will all have positive and negative values.
Not I mean like, or a specific point.
Uh-huh.
It can have like a square root, and like the root 3 over 2.
Okay. Okay, so, all right. So one thing you're saying is then, so say we've got something whose cosine is the root 3 over 2, so that would be what? A pi over 6? Cosine of root 3 over 2? And so what we have here, so let's say our eccentricity, if we're talking about a hyperbola, our eccentricity is some number bigger than 1. Let's just say our eccentricity is 2, for instance. And let's just say that our directrix is, I don't know, let's try 4. So, and let's just say that this is horizontally oriented. So here we have R is equal to E times D. So that's 2 times 4 is 8. 1, and so our directrix is positive, so it'll be a plus. And then, let's say for this particular angle, our cosine is square root of 3 over 2, but our E is equal to 2. All right? Actually, let's do it the other way. Let's assume we have an angle that has a negative square root of 3 over 2 for the cosine. So what might that be? That would be something in the second or third quadrant, right? So it might be 5 pi over 6, for instance. That would have a negative square root of 3 over 2 for the cosine. Okay? So we have 8 over 1 minus, the 2's here would cancel out, over the square root of 3. So square root of 3 is what, about 1.7 something? All right, so this is going to be 8 over negative 0.7. So we're going to have a negative value for the R. R is going to be negative in value. What happens here is because the fact that the E is bigger than 1, we'll end up having R values that are negative. For some of the angles, we'll have R values that go to the other side that are negative. That's going to generate the other section of the hyperbola. These negative R values that we're able to obtain with certain angles. Otherwise, with the ellipse and the parabola, they all get generated on the same side. The parabola is all on one side. The ellipse is all on one side. But the hyperbola, we've got 2 sections. And because the E is bigger than 1, because cosine and sine go between negative 1 and plus 1, right? So if I have some number bigger than 1 right here, and I'm combining it with 1 plus something bigger than 1 times something that can range from minus 1 to 1, I'll get negative numbers over there. We'll see that a little bit once we do an example here. All right, so now let's finally get to some examples. Actually, why don't we just take a little bit of a break, and then I've got 3 examples I want to do, and then I'm planning that's going to be it. All right. So grab some more pizza or whatever. Ty brought the brownies. Ty did. Burnt cookies are the best. Anyway,
I brought the soda.
up to a point.
people I could think of who would actually hate that. And they're all allergic to chocolate. Like,
Oh, wow. What a terrible thing to be allergic to.
they all had to try chocolate once to figure out that they were allergic to it.
Well, that's,
what they're missing too.
well, that's the only, yeah. Of course, if all of a sudden you can't breathe and break out in a rash, you might think that, well, you know what, it might turn against it.
Yeah, but EpiPen.
Huh?
Yeah.
EpiPen, right, well.
Might not be. Benefit's not so for over the risk.
Yeah, really. Well, oh, what's this? Oh.
Don't really care. We're the only Republicans nominate you on the final. And we're the only people. Even Merrimack class is canceled.
You mean the entire campus was canceled?
Pretty much. Like your other.
The teachers might be.
Yeah, a lot of the teachers just canceled the class. They just hold up class.
Well, I have an economic motive for not canceling class.
I know, I'm just saying, like, whoever board of directors or whatever could have probably noticed.
I don't know if there's only 2 full-time math people here. And one I don't think she even has classes on Wednesday. And the other one, I'm sure she's canceled her classes. I mean, I'm just sure of it.
We're just talking about not having.
No, but I know her sort of, and I'm sure she's canceled her class.
You know her well enough.
Not well enough to assume that she's done that. Now, I may be wrong, but I haven't seen her. Oh.
He had to be away for something, so he's not requiring us to go to class. He told us we couldn't cancel. He has to go because he's missed so many days. We can do it.
Oh.
My corner.
So he's already missed so many days.
He has to go.
But he has to officially have class. Otherwise, He's got a problem, huh?
Yeah.
Mm-hmm.
We told us not all done because he originally told us.
You know,
Between telling us and
there's
the day he had.
there's a lesson there in keep your mouth shut until you're absolutely sure of what it is you're saying is going to be true.
We don't really do anything like that. It's one of get assignments and then you do them outside. Get out of here.
All right. Well, let's look at some examples. Let's go back, finish this up. Some examples here. The first one's an easy example. At least I think it's easy. But actually, before I do any examples, I want you to look at just a few things in all of these 4 different equations here that we have. Okay, first of all, notice that in all 4 of the equations, the denominator leads off with a 1. All right, so we have to have that when we work with this. So if we have an equation where the denominator is not a 1, we have to divide by whatever number is needed in order to make that number a 1. All right. Notice the top is the same thing, ED. That's the eccentricity times the directrix. But that D is always positive. So the directrix could be a negative D, but that is the positive number. That number is always positive. Then below we either have E plus or minus E sine theta or E cosine theta, where E is the eccentricity. So we have eccentricity on both the top and the bottom. So let's look at this first example. 1, find the polar equation of a parabola. So right there, you know that E is equal to 1. That has its focus at 0, 0. And that's where we've had for all of these problems, we have that as the focus. And the directrix is y equals negative 6. Okay. So we have to pick which one we're going to have here. Now, this directrix is y equals negative 6. So let's try to see if we can build this thing. R equal, our eccentricity is going to be 1 because it's a parabola. I'm even going to write it up there, 1 times. Our D here up above is basically the positive magnitude associated with the directrix. So I'm not going to put negative 6, I'm going to put a positive 6. So that's 1 times 6, or 6, is going to be in the numerator. Now, below, we always have the number 1 leading off with the denominator. And then we have either plus or minus E cosine or E sine. Now, the directrix is y equals negative 6. So first of all, because it's a negative 6, that is your clue that the next thing you're going to have here is a minus sign. All right. And then we put our eccentricity. Well, that's just the number 1 in this case, and I don't even have to write that. Now, am I going to put cosine of theta or sine of theta after that number 1? I'm going to put sine of theta, and again, we're going to be, because this is y equals, and we're going to relate that to the sine function, right, for the y coordinate. So our answer here is 6 over 1 minus the sine of theta, and that's our answer. Okay? That's it. This is the easiest problem. But that's how you can, from that information, generate that equation, all right? Use the memory tips that I've given you to help you with this. All right, now let's look at something a little bit more challenging. Let me go to another piece of paper here. Number 2. For the second one, we're going to be working with an ellipse. So a conic section is given by the polar equation. R equals 6 over 3 minus 2 cosine theta. And we're asked the following questions. Find the type of conic section, find the eccentricity E, find the directrix line, find the vertices, and rough sketch. By the way, on the test, I will be providing the graph, the blank graph on it. You will have some graphs to do on the exam. Okay. So first of all, the first thing we need to do to this given polar equation is we need to get that 3 changed into a 1. All right? So I have to divide everything on top and bottom by the number 3. So that's the first thing you have to do. Divide by 3, divide all terms by 3 to get it in the right form. So now we're going to have R is equal to basically 6 over 3. I'll do this in 2 steps. 6 over 3 over 3 over 3 minus 2 over 3 cosine theta. And of course that simplifies to 2 over 1 minus 2/3 cosine of theta. Okay, so that's the first step. Are we okay with that? Top and bottom, so we get the 1 there that we need.
You don't have to like put a 1/3 out or anything. You just can just divide everything by 3.
Yeah, you have to, because we're not, if you just put, okay, the question was, can I just put a 1/3 in front? If I just put a 1/3 in front, like I think this is kind of sort of what you were suggesting. Okay. All that's going to do is it's going to change it. We don't want to change the fundamental thing. We have to divide both top and bottom by the same thing. This will change it. It'll change the numerator. Notice this would change the numerator to a 2, but it would keep the same denominator. That's not what we want. So let's put an X through that. Top and bottom, everything by whatever number is needed. Okay. Now, this number right here is the E, eccentricity. So you can read it right off of here. Eccentricity is equal to 2/3. If the eccentricity is less than 1, it's an ellipse. So that's the first question that we asked. What is the type of conic section? And actually, the first 2 questions were interrelated. And E is equal to 2/3. So actually, you have to get the E number first, and then you identify the type of conic section it is. All right. So we recognizing that E is 2/3, and we have an ellipse. All right. Now, is this going to be vertically oriented or horizontally oriented? Horizontally oriented because we have a cosine here. So let me just write this down. Horizontally oriented. Since we have cosine. All right. Now, this number up here in the numerator, this number 2, and all of these formulas here, the numerator is E times D, E times D, E times D. So this number 2 up there is equal to our eccentricity times the magnitude of the directrix, E times D. We now can solve for D because we know that E is equal to 2/3. So solve for D, since E is equal to 2/3. So we get 2 is equal to 2/3 times D, and we figure that out. We're going to figure that D is equal to the number 3. All right? Everybody get that? ED in the top. Now, the thing is, we want to figure out the directrix line equation. Okay. This is a horizontally oriented, so even now we can just do some kind of, it's going to be horizontally oriented, ellipse. Is our directrix going to be y equals something or x equals something? It's going to be x equals something because the ellipse is going horizontally. The directrix is going to be a vertical line. So the directrix, we know it's going to be x equals something, but we have this minus here in the denominator, so it's going to be x equals minus the magnitude that we came up with, -3. So our directrix line is x equals -3. Question on that? All right. Then the vertices. So let's go to another piece of paper here. So we figured out the directrix line. Now we have to figure out the vertices and a rough sketch. All right. What I want to do here is do a little table, and we'll do a rough sketch, and that's going to help us get the vertices also. So our table, our equation is what? Where is it? Here it is. R is equal to, well, you know what? Actually, for purposes of doing this table, I'm going to go way back to where we started because I don't have a fraction here. The arithmetic will be easier. It's going to be the same thing. Rather than working with what I developed, it'll be perfectly fine just to stay with what I was given originally for building this table. 6/3 minus 2 cosine of theta, and then our other coordinate, of course, is just the theta. We're going to be doing this in polar coordinates. All right. And let me start here. A rough graph. We know that right here, I'm going to have one of the focus right there at 0, 0. Okay, now when theta is equal to 0 degrees, I plug that into my R formula, and the cosine of 0 is 1. So this is going to be R is equal to 6/3 minus 2, and so that's going to be 6. Right? So let's go out here. Let's see. 1, 2, 3, 4, 5, 6. And right here is going to be a point on our curve. So this is the point 0 degrees 6 for R. Does it go the other way around, doesn't it? Yeah. R theta, 6, 0 degrees. All right. All right, let's for another one now, let's just go all the way to pi over 2, 90 degrees. So for 90 degrees, R is equal to 6/3 minus 2. Now the cosine of 90 degrees is 0, minus 2 times 0. So this is 6/3, so my R is equal to 2. So now 90 degrees is going to be down up here on this axis here, and let's just mark off 2 places, and right here is going to be another point on my curve, and we know it's going to be an ellipse. So this point here is basically 2, pi over 2 in polar coordinates. Let's just do all the angles then. Let's then do the angle pi, 180 degrees. And here we have r is equal to 6 over 3 minus 2, but the cosine of pi is negative 1. Negative 1. So that's 6 over 3 plus 2, so that's 6 over 5. So let's see, that's basically 1 1/5. So basically kind of right here, this point here is also on the graph, and this would be, 6/5 comma pi, right there. All right. And then let's do 3 pi over 2, and again, for the cosine of 3 pi over 2, we're back to a cosine of 0, so we're going to get 6 over 3, which is 2. So let's go down here, 1, 2, and then this will be a point on our curve, and that is 2 comma 3 pi over 2 right there. Okay, actually what we've done here is kind of like the 4 main points here of our ellipse. If we try to make our best effort here, and join these with something that vaguely resembles an ellipse, all right? This is what we have. Now, basically, we know that this is horizontally oriented. Oh, and let me draw the directrix while I'm at it. The directrix we found was what? X equals -3. So let's go, let's see, -1, -2, -3. So here's our directrix right here. X equals -3. All right. Okay, so the thing that I'm, besides the rough sketch, and actually for me this is a good enough rough sketch, all right, is the fact that we want to get the vertices. Now remember, for an ellipse, the vertices are along the long axis, what's called the major axis, which in this case is going to be the horizontal axis. So this point here and this point here at the very end there of that axis, this is right here in the center, are going to be our vertices. This is a vertex, and that is a vertex right there. So we can give the vertices either in polar coordinates or, if we were asked to, in Cartesian coordinates, okay? So the two vertices in, say, polar coordinates would be 6, 0 degrees and 6/5, pi, all right? If we were wanting in Cartesian coordinates, then this would be what? The x would be 6, the y would be 0, and what would this other point over here be in Cartesian coordinates? What's that? -1? No, this point right here. -6/5, right? Yeah. The x would be -6/5, and the y value would be 0. All right. So by drawing the rough sketch, it definitely want to include at least the 4 major angles. We then can figure out what the vertices are. All right? Does that make sense? So you can kill 2 birds with 1 stone. All right. The last example then is the hyperbola. So here we have number 3, and here we're given r equals 12 over 2 plus 4 sine of theta, and we're basically asked the same questions. We want to find, first we want to find the eccentricity, then we'll find the type of conic it is. Now again, the first thing we need to do is we need to make that 2 a 1, so we're going to divide everything top and bottom by 2. So that's going to be r is equal to 6 over 1 plus 2 sine of theta. All right, to get it in the right format. Okay, right here then we read that our e is equal to 2. Since that's obviously bigger than 1, we have a hyperbola. All right. Another thing we can do right off the bat is this. This number 6 up here is equal to e times d. So that is, so therefore we have 6 is equal to 2. We know that what the e is now, times d, and we can solve for what d is. D is then going to be equal to the number 3. All right, is this going to be vertically or horizontally oriented? Vertically, yeah. Vertical, because of the sign. All right, is the directrix going to be x equals something or y equals something? If it's vertical. Y equals something. It's going to have to be a horizontal line because it's a vertical orientation. So the directrix is y equals, and it's going to be a plus sign because of the plus there, and we've already figured out that our d is equal to 3. So y equals 3 is our directrix. Okay. So we've already figured out the directrix, E, the type of conic. Now we need to get vertices here. So we have to do the same kind of thing here now. We have to do a rough, and we want to do a rough sketch of this. And this is where we're going to see how in the hyperbola, because the E is a number bigger than 1, we're going to be able to get numbers on the other side to generate both of the curves. Right. Let's see here. So let's just, so I've got this set up here. And let's just start first of all with a table of some kind. So here's our theta down here. And and then our equation, I'm going to go, since I don't have a fraction here, I'm just going to go on then and just use the new version here. R is equal to 6 over 1 plus 2 sine of theta, okay? And let's just plot a few points here. So when theta is 0 degrees, the sine of 0 degrees is equal to 0, so therefore r is going to equal 6. So let's plot that point here. So here we have 0 degrees and 6 right there. Now I'm going to do a few more points with this one. When r is equal to pi over 6, okay, what do we have for our r? R is going to equal 6 over 1 plus 2 times the sine of pi over 6. But what's the sine of 30 degrees? 1/2, 1 over 2. So basically this comes out to be 6 over 1/2. So we have 6 over 1. Well, that's not right. Sine of pi over 6 is 1/2. So that's 1 plus 1, right? 6 over 1 plus 1, that's 6 over 2. We're going to get a 3. All right. So for pi over 6, we're along this ray here. And let's go to, we have a value, R value of 3. So that's going to be right there. Okay. So that's another point. Now let's go to pi over 2. So, yeah. Okay, pi over 2. And so at pi over 2, the sine is equal to 1. So this is going to be 6 over 1 plus 2, 6 over 3. So our R value is equal to 2. So this is at pi over 2. here's pi over 2 here, and here's where 2 is at, right there. Okay. All right. Then let's go, I'm going to now go to the counterpoints of pi over 6. I'm going to do 5 pi over 6. And for that, I'm again going to get the number 3. So at 5 pi over 6 over here, I'm going to go over, and I'm going to get the number 3. By the way, just to give you information on the exam, on the graphs that I want you, on most of the graphs that I want you to do, I'm going to list the points that I want you to then figure out the values for on the table. All right, so you'll have the points there, say the theta points there, and you'll then find the corresponding values for those to help plot your points. All right, so we're getting closer to the end of class than I thought. Let's go to pi here, and when we have pi, we're going to be back to 6 for our r value. So over here, we're going to have this point right here. And then when we go to let's see, 3 pi over 2, which is down here. Now this is what's going to happen there. We're going to have 6 over 1 plus 2 sine of 3 pi over 2. The sine of 3 pi over 2 is negative 1. So this is going to be 6 over 1 minus 2. 2 times minus 1. So that's going to be negative 6. So here's 3 pi over 2 down here, but I'm now going to be flipping it over here to the negative part, and that's going to be a point right there, right? Okay. Now, this is what we're going to end up having then. This is going to be the start of this whole other section up here. So basically, we're going to have up here, this whole upper part of the hyperbola, and down here, we have this whole down part of the hyperbola. Let me just tell you what these things are generated by. Starting from here, the points that are along here, I think actually this is what I want to do next before I say that. One thing that we have, yes?
Director is so much closer to the bottom, like at the hyperbola at the top. At white.
That, okay. The 2, 6, right, this is the center right here. And this is the directrix here. Actually, when you work this out, these angles up here, like you would think, okay, up here, this would correspond to like down here, all right? The thing is, this angle here is a much different angle than this angle here. And as a result, when you use the formula still works. You have a different theta that you're working with, and the formula will still work. That's all I can tell you, all right? Because, yeah, this would be the directrix. What did I say it was? Y is equal to 3 right here along this way. What I wanted to say was this. We remember that these hyperbola all have, what are called asymptotes. Hyperbolas have asymptotes. And how can we figure out the asymptote from this formula here? Here's our formula. R is equal to 6 over 1 plus 2 sine of theta. What our asymptotes are going to be our asymptotes are going to be where the r, the distance from the origin, is going to go to infinity. That's going to be where we're going to have our asymptotes. These will occur where the denominator is 0. 1 plus 2 sine of theta is equal to 0. That's when the r is going to shoot out to infinity in the various directions. So let's solve this here. So we take so to find the asymptote, we take the denominator and set it equal to 0. So that means sine of theta has to equal a negative 1/2. Okay, so when does the sine of theta equal a negative 1/2? It's going to be either in the third or the fourth quadrant, right? Well, the sine of pi over 6 is equal to 1/2 in the first quadrant. So we have to go to either the third or the fourth quadrant. So it's the sine of 7 pi over 6 that's in the third quadrant, that's going to equal a negative 1/2. And then in the fourth quadrant over here, the sine of 11 pi over 6 is also then going to equal negative 1/2. So the two angles where this is we're going to have asymptotes then are theta equal 7 pi over 6 and theta equals 11 pi over 6. Okay. Basically, here, if we looked at this thing is going to keep coming down, coming down, coming down. Here's 11 pi over 6, this straight line ray that's going down. This will get closer and closer to that ray, but it'll never touch it. But the r will keep getting bigger and bigger. In the other direction, 7 pi over 6, okay, we have the same thing happening right here also. A ray coming out that way, and again, the curve is going to keep going in that direction. And then up here, so this is from 7 pi down 2 of 2. Now this way, it's not going to be quite right that way. What we can say is this. We'll get those two angles where the denominator is is equal to 0. We can say this, that the asymptotes will be parallel to those two lines. Will be parallel to those lines. Theta equals 7 pi over 6, theta equals 11 pi over 6. Actually, the asymptotes go through the center between here and here. This is our vertex here. This is our vertex here. The center is actually right here at 4. If we draw parallel lines here, that'll also go like this, and it'll be an asymptote parallel to that 7 pi over 6. If we draw a parallel line to the other asymptote from the center, that's also going to be an asymptote that way. So it'll be parallel there. What was the other question I had here on this? What are the vertices? If we do this kind of basic drawing here, we have a vertically oriented hyperbola. Can somebody tell me what the two vertices, how we would get the two vertices here?
On the line set?
Yeah, there are going to be these 2 points right here at the bottom of the one and at the top of the other one, right? That's what you're saying? So the vertices in this case, we can look again from our drawing, and see that the first one is going to be at, if we look at polar coordinates, it's going to be at a distance of 2, and that'll be pi over 2. The other one is up here, and that's at a distance of 6, and that's also at pi over 2. Of course, we got it from -6, 3 pi over 2 is how we had gotten it. If we want to look at Cartesian coordinates for our vertices, this would be the point, let's see, y is 2, x is 0, 0, comma 2. Here y is 6, x is 0, 0, comma 6. So from the drawing, we can see that at the top and bottom of those two shapes, that's where we're going to have our vertices. The one other thing I wanted to say on this is how are all of these lines really generated by this one equation? This whole part of the line here on the bottom part, if we go from basically 11 pi over 6 all the way to 7 pi over, if we go this direction, and I guess I really want to say negative pi over 6, keep traveling along, and all the way this way to 7 pi over 6 in our formula, that's going to generate all of these down points here. Up here, basically for up here, it's going to be starting in this direction here, going around like this, and these are going to be generated starting at 7 pi over 6 all the way to 11 pi over 6 over here. 7 pi over 6 going all the way to 11 pi over 6. So basically, because the r can go flip back to being negative, we get these upper points, and then we can have these bottom points also. All right. It's a little bit tricky. I tried to graph this on Maple, and because it goes out infinitely, it just squished everything into a straight line or something. It just messed the whole thing up. Again, you'll be directed as to the points you need to put on the graph. These types of problems here that we just did, and the things that you're going to see on the practice set, are basically the kinds of things you'll have then for this section. All right? It's basically identifying the eccentricity, the type of conic it is, how it's oriented, and what its directrix is, and doing a rough sketch. Okay, so I think with doing the homework and the test and practice questions, you'll be okay. All right, boy, I thought I was going to end up a lot earlier than this. That's it. Thanks, guys, again for being here.